Okay, so let's proceed with some calculations. Question here that reads, you can write the question down for your benefit. A buffer solution was prepared by dissolving 0.0112 moles of sodium ethanoate. So you have 0.0112 moles of sodium ethanoate, which is the salt. Remember we said a buffer is prepared by mixing a salt of the acid and the acid. So here you have the salt of the acid. So this 0.0112 moles of sodium ethanoate was dissolved in 100 cubic centimeters of a 0.0520 moles per cubic decimeter ethanoic acid. Take note, this one is the number of moles, but this one is concentration, it's moles per cubic decimeter of ethanoic acid. So this is the concentration of the acid. And you are told that the acid dissociation constant Ka for the acid has the value 1.74 times 10 to the power minus 5 moles per cubic decimeter at 25 degrees Celsius. So Ka values are given at a specific temperature. Don't be surprised when you see temperature. And let's go early to and talk about the acid dissociation constant. So when an acid dissociates, let's suppose we have an acid HA. This could be your ethanoic acid, which dissociates to form H plus ions and A minus ions. In this case, this is representing the conjugate base. This could be your ethanoate ions. If you wanted to calculate Ka, the acid dissociation constant, you would say the products which are your H plus, we are coming from this side to this side, so your H plus higher product and your A minus higher product. So you're going to say product, the products of a reactant, and you're going to multiply the product of the concentrations. So you multiply the concentration of H plus, concentration of A minus, and divide by the concentration of the acid. So this Ka value will tell you the extent of dissociation. It will tell you whether your equilibrium is biased towards the right or the left. So when you have a larger Ka value, it means that your equilibrium is biased towards the right hand side, meaning that we have more of these products in solution, meaning that your acid is strong. It quickly dissociates to form for you H plus and A minus, or it dissociates. A large fraction of the acid molecules are going to dissociate to form for you the H plus and A minus. So you would have a larger number on top here and a smaller number at the bottom, meaning that we are having less and less of the acid to form H plus and A minus. So that means that's a strong acid. The reverse is true. When you have a smaller Ka value, that's a weak acid. So this is acid dissociation constant. It tells you, it gives you a picture of how strong your acid is and the extent of dissociation of the acid molecules. So if you rearrange this expression, in order for you to calculate pH, the question is calculate the pH of the buffer. The question really is calculate the pH of the buffer. So if you wanted to calculate pH, you need to know the concentration of hydrogen ions. So if you rearrange this equation, you would come up with H plus, concentration of H plus ions is equal to Ka times the concentration of the acid over the concentration of the salt. So this is the equation that is just a result of rearranging this. So this equation should not be intimidating. And you should also know that there is another equation that is used to calculate pH. pH is equal to negative log concentration of H plus ions. So once you can find the variables here, then it becomes easy for you to figure out the concentration. So let's go back to the question. It says we need to know the number of moles of the salt. We need to know the number of moles of the acid that we had or that we have in this buffer. So number of moles, we are told that we added 0.012 moles of sodium ethanoate. So this becomes the concentration of our salt in the equation. This is where, remember, this is where the conjugate base ions are coming from. They're coming from the salt. And it's also important to take note that there's an assumption here. The acid itself can dissociate. Remember, say this is a weak acid. It can dissociate to form H plus and A minus. So if it's ethanoic acid, it can dissociate to form for you the ethanoate ions. But these are negligible. Remember, it's a weak acid. So they are not included. So we assume that all the ethanoate ions are going to come from the salt of the acid. It's an assumption. All of the molecules of the conjugate base are going to come from the salt, since the acid is weak and it doesn't fully dissociate. So the concentration of the salt goes directly here. Now the concentration of the acid is assumed to be the original concentration that you had. So let's see here. And if you know these calculations, there is a short way of calculating where you can just plug in moles here. That's called the moles method. You can put concentrations or you can put moles. We'll look at that in another video. But in this case, we're just going to plug in the moles directly. So let's find out how many moles of the conjugate base or the salt we had 0.0112. How many moles of the acid? We're going to assume the original number of moles as if the acid didn't dissociate at all, since it's a weak acid. So we're going to calculate and say concentration times volume to get the number of moles of the acid. So our concentration was 0.0520 times the volume of 100 cubic centimeters converted to cubic decimeters here. So we get 5.2 times 10 to the power minus 3. So with this, now we can just go and substitute into our formula and find the concentration of H plus ions and substitute those into this formula and find our pH. So let's do that in the next video.